Welcome to this video on equilibrium in 3 dimensions. In this video, we will solve some example problems by using a software. If you're not sure about the theory of equilibrium in 3 dimension, you should watch this video before watching the current video. Our first problem. A 200 pounds uniform door is in contact with a floor stop at C this is C and is suspended from two rollers A and B in a rail which is horizontal here. Determine the horizontal forces applied by the rollers on the door. Even if you know all the theory and all the equations, solving three-dimensional equilibrium problems will require some thought. Let's look at the roller at A. The roller at A, a push force and a contact force. The contact force is vertically upward because the roller is resting on the rail, and there is another push force just because the roller is sitting on this notch. It cannot move back and forth like that. So just because it cannot move back and forth like that, it also applies an X force, and the contact applies a Z force. To find the location of the roller A, you have to go up 10 feet, which is along the Z direction. So the Z coordinate of the roller is 10. Then you will have to move 3 feet along the y-axis. Location of the roller along y-axis is 3. And then you will have to come out 6 inches along the x-axis. So the z coordinate, x coordinate of the roller is 0.5. Similarly for roller at B, roller or floor stop at C applies a contact force only in the x direction, and it's applied at 0, 5, 0. Z coordinate is 0, x coordinate is 0, y coordinate is 5 feet. The weight is at the center of mass. The weight of 1200 pounds is acting downward. Hence, the Z component of the weight is negative 1200 pounds, and it's applied through the midpoint of the door. The door is 3 feet plus 10 feet plus 3 feet, 16 feet wide. So the y coordinate of the center of mass is 8 feet. The door is 10 feet high, so the z component of the center of mass is 5 feet high, and that's why we get here a 0.85. Now let's solve this problem by using the software. We open the software, start it, pick equilibrium in 3D, and now we will enter the data for the roller at A, roller at B, stop at C, and the weight of 1200 pounds. First roller, add support, location, the name of the roller is A, and it applies two forces, one along x-axis, one along z-axis. We add another roller. This is the roller at B, 0.5, tab 13, 10. The name of the roller is B, and it applies forces at x-axis and z-axis. Roller is added. Then the stop at C is also a roller. We add that support at location. Its name is C, but it applies a force only along the x-axis. We add that. All supports added. We click on all supports added. Now we want to add the load, which is a force. So we add the load. The location is components are 0, 0, negative 1200. We apply the force. All loads added. We get the equations of equilibrium. There are 5 equations. 1, 2, 3, 4, 5 equations, whereas the y component of force balance is 0 equals 0. There are no forces in the y direction. We have 5 equations and 5 unknowns: ax, bx, cx, az, and bz. You have to solve the 5 equations for the 5 unknowns. Now let's look at the second problem. Again, it's a rectangular plate. Which is supported by a ball socket joint at O. So this is O. A roller at A, a horizontal spring here which applies a force along the x-axis, and a cable EF. So we have a cable EF, a ball socket at O, a spring at S, a roller support at A, and the weight at center of mass. The cable is EF, where you can see E is coordinate of E is 18 inches along the x-axis, (36 inches along the y-axis, and 0 inches along the z-axis. F is starting from the origin. There is no x displacement. We go up 16 inches along z-axis, come out 16 inches along the y-axis. The ball socket location here, the total width is 36 inches. but the ball socket is 6 inches back, so the location of the ball socket is 30, 12, 0. We get the 12 from here, the displacement along the y-axis. Spring at S, we can model the spring as a cable, but we are going to model the spring as a pin, just because the spring is aligned with the x-axis. It applies only an x force, and it's located at 36 along x and 36 along y. The weight at center of mass is -100 because it's downward, and its location is at the midpoint of the plate, which is 18, 18, 0. So now we enter the data. First we pick a cable, add the support. Start location is 18, 36, 0. The name is E. The end point of the cable is 0, 16, 0, and the name of the endpoint is F. We add the cable, then we add the ball socket, add support, put location, add name, ball socket is added. Spring S, as we talked about before, we could have modeled the spring as a cable, but we decided to model the pin as we wanted to model the spring as a pin with only an X force. Add support. The location of the spring is 36, 36, 0. Name is spring S. Now the roller at A, now we add the roller. The location of the roller is the origin. The name of the roller is A. And the roller applies a force only along the z-axis. All the supports are added. We add a force. Force location is the midpoint of the plate. And the weight is acting downward. All loads added. These are the equilibrium equations, but you have to remember that Sy and Sz are 0. If you do not count Sy and Sz, then you have 6 equations. Do not count Sy and Sz. You have Ox, Sx, Oy, OZ, AZ, OY, AZ, you will see that this equation has 6 unknowns. And we can find those 6 unknowns from the 6 equilibrium equations. Remember, SY and SZ are 0. Now let's look at the third problem. A 13 kg plate, which is vertical here, is attached to a vertical rod is also attached to a cable CD. We have a thrust bearing at A, a journal bearing at B. The weight which is acting downward is given in kgs, which you will have to convert to newtons by multiplying by 9.81. And on top of that, there is a couple of 120 Newton meters applied on this rod. So the total loading consists of the weight of the plate and the couple. We are going to insert all the lengths in millimeters, so do not forget to convert this from 120 Newton meters to 120 Newton millimeters, which is easy. We just have to multiply by 1,000. First, we introduce the thrust bearing. Its location is we give it a name A. A thrust bearing applies forces in all 3 directions, AX, AY, AZ. So you can see AX, AY, AZ appear in the equilibrium equations. We add a journal bearing at the support. Its location we give it a name B. This journal bearing applies forces only in the X and Y directions. Add it. Now we have to add a cable. The cable is attached to the plate and the name of the point where it's attached to the plate is D. The other end and name of that end is C. We add the cable and the cable enters the equilibrium equations. All these supports are added. First, add the weight as a force, add load. The location is through the midpoint of the plate, and the value is, remember, we changed the 15 kg into newtons by multiplying it by 9.85. And now we apply the force. Now we add the couple applied. The components are Remember, we have to change the units from Newton meters to Newton millimeters. So it becomes 120,000. The location of a couple is unimportant. We apply the moment and then we click on all loads added. We get the 6 equations of equilibrium. The unknowns are AX, BX, tension along the cable DC, AY, AZ, BZ. So AX, BX, AY, AZ, BZ, and the tension in the cable DC. So there are 6 unknowns. You solve these 6 equations to find the 6 unknowns. That's the conclusion of this lecture.